So we can prepare a small volume of the injection or the sterile product so as to not to contain anything left over for storage. If there is material that's going to be left over for storage, then you better have some preservative, because during storage there's always a likelihood of microorganisms multiplying. When materials can be refrigerated, this is particularly something that is indicated in the manufacturer's package insert. Sometimes solutions and injections containing um, active ingredients um, that may be prepared in a large volume but may be stored in a refrigerator may be given an extended beyond use date. That's an instance where you may not contain a preservative in the final solution, but it's still good to use over the period of time that is indicated by the manufacturer. And also, preservatives, when they're contraindicated, we may have to use a very short beyond use date. So beyond use date is a date that is arrived by the pharmacist based upon information available from the manufacturer, as well as literature that clearly indicates for how long and in what conditions can the product be stored and still be used without any harm to the person who's using this, even when a preservative is not present in the final formulation. Uh, some properties as far as an ideal preservative is concerned. Preservatives should be very effective at low concentrations, because preservatives are chemicals that destroy microorganisms, that degrade microorganisms, that prevent microorganisms from multiplying. It's always best to keep its concentration at low levels. And that's because these chemicals could be potentially be damaging to healthy cells within the person who may be taking this formulation. Additionally, it's best to have a broad spectrum of activity. That means uh, it's ideal for a preservative to be active against gram-negative and gram-positive bacteria as well as fungi. You cannot add a preservative specifically for a gram-positive organism and then a gram-negative organism and then fungi, because these will add to the total chemical load of the final preparation, and they can be harmful to the person who's using this. It should also be chemically stable over a wide pH range and temperature. It should be soluble. If the preservative precipitates out of the solution, then it will lose its potency, preservative effect, and hence will thereby not be able to prevent microorganisms from multiplying and thriving in the solution. And so it has to be perfectly soluble in the concentration range that it is being used. The preservative should be free from objectionable odor, taste, color, or stinging. It should be non-toxic and non-sensitizing both internally and externally at the required concentration. It should be inexpensive, relatively inexpensive. It should be physically and chemically compatible with containers and closures. If it's not physically and chemically compatible with containers and closures, what would happen is the preservatives could be absorbed or denatured or maybe degraded by the container and closure systems, thereby rendering it ineffective. There are numerous examples for USB NF preservatives: benzalkonium chloride, benzalkonium chloride solution, benzalkonium chloride, benzoic acid, benzyl alcohol, butyl paraben, cetylpyridinium chloride, chlorobutanol. All of these are examples that are given in the USB NF. Okay, we'll start off with different kinds of preservatives that are used in different types of dosage forms. We'll start with preservatives used in oral dosage forms. Alcohols and glycols. Ethyl alcohol, also known as alcohol USB, could be available as dihydrolyl alcohol USB, dihydrolyl alcohol injection USB for use in parenterals, and injectables, as well as diluted alcohol. All of these are different types of ethyl alcohol that are available for use as preservatives. The effective concentration depends on pH and amount of free water. So, what is meant by free water is that when water is present in formulations, it can be present in three different types: free water, also known as bulk water, interfacial water, and tightly bound water. So, water in formulations can be present in three different kinds. Interfacial water and tightly bound water are not capable of sustaining microbial growth and so are not of concern. It's the free water that is present in formulations that can actually sustain microbial growth, and hence free water concentration may have to be determined when using ethanol as the preservative. If you take into account the total water in the formulation, you may you may be overestimating the amount of alcohol that is to be used, and so always the amount of free water will have to be determined when using alcohol as a preservative. Typically 15% to 17.5% of free water is the amount of ethanol that is necessary to be used as a preservative. 5 to 10% of the volume of compound preparation is what is typically utilized. An example formulation is written in the slide: mineral oil, emulsion USP, where mineral oil 500 ml, acacia, syrup, vanillin, and alcohol is used as a preservative, and purified water is the external phase. This is an example for a water and oil emulsion that contains alcohol as the preservative. Here are some examples for alcohols and glycols type preservatives. Propylene glycol USP, the effective concentration is about 10% weight per volume. Up to 30% weight per volume can inhibit mold growth. Propylene glycol has also been found to potentiate other preservatives. 2 to 5% enhances the effect of methyl and propylparaben. There are entirely different category of preservatives. Then glycerin, the effective concentration is greater than or equal to 50%, used mostly in combination with alcohol. Now, ethanol, I forgot to mention this, ethanol actually produces its antimicrobial preservative effect due to its dehydrating effect. Ethanol can actually pull water away from microorganisms, thereby dehydrating its membranes as well as intracellular contents, causing death to the microorganism. That's how it produces its antimicrobial preservative effect. Alcohols and glycols, propylene glycol or glycerin, on the other hand, are also capable of drawing water out of the microorganism. Here, they are able to bind water molecules, preventing microorganisms from thriving, and that's how it exerts its antimicrobial preservative effect. Then benzyl alcohol NF. I'm not going to hold you responsible to memorizing the solubility or anything, but it's very effective bactericidal. Bactericidal means something that kills bacteria at 1 to 2% concentration. It's a very sharp burning taste, and hence you should think about this when utilizing whether you can actually utilize benzyl alcohol in an oral formulation or not. I mean, if it has a very sharp burning taste, it's not going to be palatable. Most effective below a pH less than 5, minimal activity about pH 8. It's incompatible with methyl cellulose and polysorbate 80. Now, benzyl alcohol is a preservative that is contraindicated. And is an example for a preservative that is present in irrigation solutions that were used in neonates that led to infant fatalities. And it came to be banned, and that incident actually led to banning of preservatives in solutions or any preparation that is used in neonates. Benzyl alcohol was the culprit that led to death of several newborn infants when it was used in the irrigation solutions. Benzyl alcohol actually is chemically similar in terms of chemical structure to substrates that are utilized during nucleic acid synthesis, and hence benzyl alcohol can actually decrease or inhibit nucleic acid synthesis by its presence, and that's how it exerts its antimicrobial effect. Benzoic acid, very similar to benzyl alcohol, except for that it has a carboxylic acid functional group as well. Benzoic acid is available as a sodium benzoate salt as well as potassium benzoate salt. It's very soluble in water. Effective concentration is 0.1 to 0.3% concentration, much better in terms of effectiveness at much lower concentration compared to benzyl alcohol. It's ineffective above a pH of 5 because above a pH of 5 the carboxylic acid functional group will be ionized more, and it's ideal that you have a greater percentage of or a greater fraction of the benzoic acid molecules be unionized to exert its antimicrobial preservative effect. Other examples for organic acid type um, preservative, sorbic acid or potassium sorbate, quite soluble in water. Effective concentration is much less than benzoic acid, 0.05 to 0.2%. It's very widely used because it's one of the least toxic preservatives that is currently available in the market. Sorbic acid and similar type of preservatives actually inhibits carbohydrate metabolism. Carbohydrate metabolism is a route through which microorganisms obtain energy, and sorbic acid and similar preservatives inhibit carbohydrate metabolism through inhibition of certain enzymes in the metabolic pathway, preventing microorganisms from deriving energy by metabolizing sugars, and this will lead to eventual microbial death or limit microbial multiplication, and that's how sorbic acid exerts its antimicrobial preservative effect. Para-hydroxybenzoic acid is another example for an organic acid. Para-hydroxybenzoic acid derivatives are also known as parabens. Some examples are methylparaben, methylparaben sodium, propylparaben, and propylparaben sodium. If you were to compare the water solubility of methylparaben and propylparaben, you'd see that since propylparaben has one additional carbon group, carbon in the functional group in the chemical structure, methylparaben will be expected to have a greater water solubility than propylparaben, and hence in many formulations methylparaben and propylparaben will be used in combination because methylparaben will preserve the water component and propylparaben will preserve the oil component. These preservatives are useful at very low concentrations. Methylparaben, for example, is useful at 0.05 to 0.25% concentration. Propylparaben, on the other hand, is useful at 0.02 to 0.4% concentrations. Para-hydroxybenzoic acid also has some structural similarity to chemicals that are utilized during nucleic acid synthesis, and hence parabens are capable of inhibiting nucleic acid synthesis, and that's how they produce its antimicrobial effect. Now some examples for preservatives that are used in topical products. Alcohols, ethyl alcohol, we talked about that. Isopropyl alcohol is something that was not discussed earlier. Isopropyl alcohol, similar to ethyl alcohol, also produces dehydration. It cannot be used internally due to its toxicity. It's safe for use externally, and hence is used in all those antimicrobial gels, antiseptic gels that are commonly used to uh, sanitize our hands. Effective concentration is 5 to 10%. Propylene glycol, glycerin, benzyl alcohol, phenoxyethanol, all of these are examples for alcohol and glycol type preservatives that are used in topical products as well. Other examples include organic acid, benzoic acid and sorbic acid. Both of these organic acids prevent or inhibit and microbial cellular metabolism, particularly carbohydrate metabolism, preventing the organisms from utilizing sugars to derive energy, and that's how it exerts its antimicrobial effect. Then esters of hydroxybenzoic acid or the parabens are also used in topical products, and I'd already talked about this earlier. Now, another very controversial type of preservative that is utilized uh, in different formulations are the organic mercury derivative. There are different examples for these: phenyl mercuric acetate (PMA), phenyl mercuric nitrate or PMN, thimerosal topical solution, and thimerosal tincture. These are highly effective, very effective, in extremely low concentrations. For example, PMN you can use in topicals in 0.002 to 0.01%. In ophthalmic solution, 0.002 to 0.004%. So far, the effective concentration in which these preservatives are effective is much better than all of the other examples that we have seen so far. Thimerosal can be very effective in extremely low concentration, 0.001 to 0.02%. So that's a very small amount of preservative that is extremely effective in preventing microbial growth. And hence these were used widely in all kinds of different formulations. However, because mercury and the organic mercury derivatives are chemically very reactive, they have numerous incompatibilities. So the components, the formulation components, will have to be very carefully evaluated to ensure that the product that is going to be utilizing organic mercury derivatives will not be incompatible with the excipients that are also used in conjunction. Uh, the problem with organic mercury derivatives because is uh, the 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 uh, the concerns related to mercury toxicity, and perhaps the oldest example for when mercury was found to be toxic was the Minamata tragedy that occurred in Japan when an industrial facility released large amount of mercury into the to water bodies that eventually led to accumulation of mercury in fish and other and other fauna in the water bodies that was being harvested by people who lived along the river, and they consumed the fish as well as other material that they extracted out of the river, and because mercury had accumulated from the industrial effluents that was released into the river, people started to show severe forms of mercury toxicity. It's perhaps one of the most notorious industrial toxicity tragedies ever. And this led to numerous deaths and fatalities, as well as teratogenic lifelong disabilities, and so on and so forth. And hence, this is used as an example for when mercurials has been found to exert its immense toxicity in human beings. However, it was later on proved that organomercurials, that means mercury containing organic compounds, although in Minamata tragedy, what was released to the river was inorganic mercury. It was later found that organomercurials, that means mercury containing compounds, organic compounds, can also possess potential neurotoxicity, and hence this led to thimerosal being removed or reduced to trace amounts in all vaccines recommended for children 6 years and younger. However, inactivated influenza vaccine is an exception. It still contains small or trace amounts of mercury. Now, mercury can prevent microbial growth in the event the vaccine is contaminated. It's used in multi-dose vials, but because of the concerns related to toxicity and neurotoxicity of mercurials, additional preservatives during manufacture has been decreased, and uh, the use of preservatives necessary in multi-dose vials because bacterial contamination can occur even in the presence of preservatives if wrong technique is used. If wrong technique as well as wrong usage during the usage of the product leads to excessive contamination of the product. If preservatives are present, even when preservatives are present, it can actually lead to uh, contamination and microbial growth. So even when preservatives are present, these products formulations will have to be very carefully handled. Now, as far as thimerosal is concerned, 50% of the molecular weight is contributed by mercury. It is typically metabolized to ethyl mercury and thiosalicylate. Ethyl mercury is not the same as methyl mercury, which is actually is a metabolite produced by in the body when it is exposed to inorganic mercury. However, it's very effective. Thimerosal is very effective in 0.001% to 0.1% concentrations. A simple math is 0.01% thimerosal will be equal to 50 microgram thimerosal in zero point 0.5 milliliters, which will be equivalent to 25 micrograms mercury in zero point 0.5 milliliters of the formulation. Most mercury in nature, though, is in the form of inorganic mercury salts, and mercury contamination in aquatic food chain is in the form of methylmercury, and hence typically aquatic food, such as fish and other substances that has a likelihood of accumulating inorganic mercury due to its normal exposure to mercury that is present in nature or introduced in the nature through effluents from industrial processes. There's always a limit as to what portion of a particular food can be consumed that is obtained from water bodies. For example, large fish tend to accumulate as well as feed on smaller fish, and hence large fish will contain the largest percentage of mercury in its per ounce body weight, and hence the amount of large fish that can be consumed is limited as per EPA guidelines. Mercury accumulation in aquatic food can be through exposure to effluents that are released into water bodies, as well as things that are drained from naturally through water drainage from land into water bodies. And this type of mercury that is accumulated in aquatic food can be very easily absorbed and ingested, and hence has to be very carefully monitored. Now, the mercury that is ingested in this manner is very difficult to eliminate once it is ingested into the body, and hence that's hence the reason for limiting the portion size of such type of food that can be consumed over a particular time period. Human exposure is primarily through seafood. As I mentioned earlier, mercury accumulates along the food chain. It accumulates in small organisms. The small organisms are eaten by larger organisms, and so on along the food chain. And hence, the largest organisms, the largest fish, contains the largest amount of mercury of all. Now, scientifically, methylmercury has been found to be a neurotoxin. That means it actually affects the neuronal tissues, such as, say, spinal cord, nerves, and brain. And hence, because of this capability for it to exert neuronal toxicity, fetuses are more sensitive than adults, and hence maternal exposure during pregnancy has been found to result in neurologic injury in infants, such as neurodevelopmental disorders, sensory disorders, motor neurological dysfunction, and so on. All of this has been documented in populations that have been exposed to high levels of mercury. However, long-term epidemiological studies were inconsistent. Safe levels have been established for daily exposure of mercury and organomercurials. As far as EPA is concerned, safe levels is about 0.1 microgram per kilogram per day. Uh, World Health Organization, however, has a higher limit of 0.47 microgram per kilograms per day. National Academy of Sciences, or NAS, which is a premier scientific body in the United States, has actually ratified the EPA levels. Mercury exposure guidelines currently that are used are based on methyl mercury. Thimerosal is an ethyl mercury derivative. There's no definitive data on ethyl mercury. However, FDA considers ethyl mercury equivalent to methyl mercury, and hence the same guidelines apply to ethyl mercury type derivatives as well. A very common type of reaction that can occur when vaccines or other injectables that contain thimerosal are administered is a delayed type local hypersensitivity reaction where there is some sort of redness and swelling at the injection site. However, reactions are mild and can only last a few days, and it'll be gone after that. Acute mercury toxicity has been well documented. 3 milligrams per kilogram to several hundred milligrams per kilogram has been found to be acutely toxic. Maximum tolerated dose in animals about 20 milligrams per kilogram in rabbits, 45 milligrams per kilogram in rats, and ethyl mercury has been found to be less toxic than methyl mercury, but as I told earlier, FDA considers both to be equivalent. In recent studies, when I say recent, about 2002, examined mercury levels in blood and other samples from infants who received thimerosal-containing vaccines in a lot of countries across the world, and blood levels were found not to exceed safety guidelines. Mercury was cleared from blood faster than predicted for methyl mercury when thimerosal was present in these vaccines. However, significant amount of mercury was recovered from stool samples during the study period. And so the FDA Modernization Act of 1997 they did a comprehensive review of use of thimerosal in childhood vaccines. The amount of mercury from ethyl mercury received was considered to be comparable with methyl mercury. In some cases, cumulative levels exceeding EPA recommendation was detected. The NIH, CDC, HRSA, and American Academy of Pediatrics urged vaccine manufacturers to reduce or eliminate thimerosal. Now, thimerosal has been eliminated or reduced to trace levels. What is meant by trace level is that trace level is equal to 1 microgram of mercury per dose or less. Additionally, National Vaccine Advisory Committee on Immunization Practices of the CDC, and Immunization Safety Review Committee, or IOM, reviewed thimerosal safety in vaccines. Incidence of autism, which is a neurodevelopmental disorder, and thimerosal exposure was also evaluated. It was found that no change in autism rates was found to be relative to amount of thimerosal during the first 6 months. However, there was some weak association with ADHD. That means there was some correlation between presence of thimerosal and ADHD incidence. And so, Immunization Safety Review Committee of 2001 convened to review selected issues related to immunization safety. The reviews were complete in 2 areas. They tried to see if there was any potential link between autism and MMR vaccine. Also, They also investigated if there was any potential relation between thimerosal use in vaccines and neurodevelopment disorders. The hypothesis, a very controversial hypothesis, was autism is a novel form of mercury poisoning. This hypothesis was made by R. Bernard of Cure Autism Now, based on a comprehensive scientific literature review. However, this was discredited and has been found not to be scientifically valid. However, the Immunization Safety Review Committee of 2001 led to the following conclusions. They found that there was not enough evidence to either accept or reject a causal relationship between thimerosal exposure from childhood vaccine and neurodevelopmental disorders such as autism, ADHD, and speech or language delay. However, they suggest that additional studies are needed. It is, though, biologically plausible that exposure to thimerosal containing vaccines and incidence of neurodevelopmental disorders could be correlated, and hence they recommended that thimerosal as well as other mercury-containing preservatives be limited or decreased or completely phased out from formulations. The Immunization Safety Review Committee of 2001 recommended that they should try to remove thimerosal from vaccines. It'll be a wise measure to follow. Full consideration was to be given to remove thimerosal from any biological product that is going to be given to children, infants, and pregnant women. Now, in 2004, based on epidemiological evidence from the US, Denmark, and the UK and Sweden, a multi-country study, they rejected any causal relation between thimerosal-containing vaccines and autism. The hypothesis generated regarding any relationship was considered to be only theoretical. So that's as far as mercury compounds are concerned. Now, coming to very commonly used other type of compound, which is the quaternary ammonium compound, benzalkonium chloride NF, benzalkonium chloride solution NF, benzalkonium chloride USP, benzalkonium chloride topical solution USP, benzalkonium chloride tincture USP, cetyl pyridinium chloride USP, cetyl pyridinium chloride topical solution USP. These are some examples for quaternary ammonium compound type preservative that are used in formulations. Benzalkonium chlorides as well as quaternary ammonium compounds are very soluble in water. The effective concentrations are quite low, 0.004 to 0.02% in some cases. Because quaternary ammonium compounds has a positively charged nitrogen, it leads to a lot of incompatibilities, and so excipients that are present in different formulations can actually impact the effectiveness as well as reactivity of the quaternary ammonium nitrogen, can lead to a lot of incompatibilities with other excipients that are present in formulations. Hence, the presence of these excipients will have to be evaluated and compared against the reactivity to quaternary ammonium compounds when being formulated. Now, as far as the how quaternary ammonium compounds um, produce antimicrobial effect, quaternary ammonium compounds are very good surface active agents, and it has a positive charge, a positively charged nitrogen in the molecular structure. And so these molecules are capable of partitioning into the membrane, cell membrane, and actually cause inequilibrium, actually disrupt the membrane equilibrium, and hence can actually cause disruption and rupture of cell membranes, leading to cell death. And that's how quaternary ammonium compounds exerts its preservative effect. Here are some examples for different types of preservatives that are used in ophthalmic products. Most of these excipients have already been discussed earlier on. One particular example that was not discussed earlier was chlorobutanol. It's an alcohol type preservative. Its effective concentration is about 0.5%. It's incompatible with silver nitrate and sodium sulfonamides. It cannot be used in oral preparations because of its camphor-like odor and taste, and hence, because of its bad odor and taste, it cannot be used in oral formulations. Okay, that's the end of this lecture. Thank you for your attention.